Hello everyone, this is Siddiqur Rahman and welcome to the first lecture of the 10th week. Let's explore the learning objective of this lecture. That's why we need to move into the next slide. By the end of this lecture, you guys will be able to describe about registers. Not only describe, you can say not only describe, but you can know, or you guys will know about the overview of registers as well as shift registers. After learned, you can describe about registers as well as shift registers. Now we need to move into the next slide to explore what kind of topics are gonna covered by this lecture. So let's move into the next slide. This slide represents the overall outline of this lecture, and you guys will know from this lecture several things, such as first you learn general overview of this lecture. After that you may learn the overview of registers. After that you may learn overview of shift registers. After this you may learn modes of shift register. After that you may learn how to design 3-bit serial in serial out shift register, as well as how to design, or you can say the design mechanism of 3-bit serial in parallel out shift register. After the design mechanism, you may learn, or you guys will learn some of the advantages of shift registers and what is the drawback of this type of register. And lastly, you may learn some of the applications of the shift registers. Now time has come to explore the general overview of this lecture. That's why we need to move into the next slide. Flip-flops can store a single bit of binary data, which means 1 or 0. But if we need to store multiple bits of data, we need multiple flip-flops. As a single flip-flop is used for 1 bit storage, n number of flip-flops are connected in an order to store n bits of data. In digital electronics, a register is a device which is used to store the information. Flip-flops are used in constructing registers. I repeat it again. Register is a group of flip-flops which is used to store multiple bits of data. For example, if a computer is to store 16-bit data, then it needs a set of 16 flip-flops. The input and outputs of a register are maybe serial or parallel based on the requirement. The series of our data bits are stored by registers, which is called byte or word, where a byte is collection of 8 bits and a word is a collection of 16 bits, which is equivalent to 2 bytes. When a number of flip-flops are connected in series, this arrangement is called a register. The stored information can be transferred within the registers. These are called as shift registers. A shift register is a sequential circuit which stores the data and shifts it towards the output on every clock cycle. Now time has come to explore the general overview of registers. That's why we need to move into the next slide. A register is a memory device which can be used to store more than 1 bit of information. A register is usually realized as several flip-flops with common control signals that control the movement of data to and from the register. Common refers to the property that the control signals apply to all flip-flops. In the same way, a register is a generalization of a flip-flop. Remember this line. carefully. I repeat it again for you guys. A register is a generalization of a flip-flop. Where a flip-flop stores one bit, a register stores several bits. The main operations on a register are the same as for any storage devices, such as load or store, which means put new data into the register. Another one is read. Retrieve the data stored in the register, usually without changing the stored data. So now we need to move into the next slide to explore the general overview of shift registers. The shift register is another type of sequential logic circuit which can be used for the storage or the transfer of binary data. This sequential device loads the data present. I repeat it again. This sequential device loads the data present on its inputs and then moves or shifts it to its output once every clock cycle, hence the name shift register. So from this paragraph you guys will know how shift register is named. Okay, so let's move into the next paragraph. A shift register basically consists of several single bit D type of data latches, one for each data bit, either a logic 0 or 1, connected together in a serial type daisy chain arrangement so that the output from one data latch becomes the input of the next latch, and so on. Data bits may be fed in or out of a shift register serially, that is one after the other from either the left or the right direction, or all together at the same time in a parallel configuration. Now we need to move into the next slide. The number of individual data latches required to make up a single register device is usually determined by the number of bits to be stored, with the most common being 8 bits, which is equivalent to 1 byte. Wide constructed from 8 individual data latches. Shift registers are used for data storage or for movement of data, and are therefore commonly used inside calculators or computers to store data such as two binary numbers before they are added together, or to convert the data from either a serial to parallel or parallel to serial format. The individual data latches that make up a single shift register are all driven by a common clock, which is known in short as CLK, signal making them synchronous devices. Now time has come to explore how to design 3-bit serial in, serial out. So let's move into the next slide to explore the design. Before, as I said from in previous slide, that we need to learn the design mechanism, but before going to design mechanism we need to learn some of the modes of shift registers. So this slide represents the modes of shift register. So let's begin. Shift register ICs are generally provided with a clear or reset connection so that they can be set or reset as required. Generally, shift registers operate in one of 4 different modes, with the basic movement of data through a shift register being, such as serial in, serial out shift register, which is in short, or which is named as shortly SISO, which is CISO. Next one, serial in, parallel out shift register, which is in short, or which is also known as shortly SIPO. Next one, parallel in, serial out, which is also I repeat it again, parallel in, serial out shift register, which is also known as PISO. Last one is parallel in, parallel out, which is also known as PIPO shift register. Let's move into the next slide to explore some of the I repeat it again. Let's move into the next slide to explore, or you can say to know, the short description of these individual modes. So let's move into the next slide. First, serial in, serial out, shift register. The data is shift serially in and out of the register, one bit at a time in either a left or right direction under clock control. Next one, serial in, parallel out, which is in short SIPO register. The register is loaded with serial data, one bit at a time, with the stored data being available at the output in parallel form. Next one, parallel in, serial out, shift register. The parallel data is loaded into the register simultaneously and shifted out of the register serially, one bit at a time under clock control. Next one, parallel in, parallel out, shift register. The parallel data is loaded simultaneously into the register and transferred together to their respective outputs by the same clock pulse. Now we need to move into the next slide. The effect of data movement from left to right through a shift register can be presented as follows, which is represented in this slide, and you may find this in this figure there are four sections or four sides: left side, right side, upper side, as well as lower side or down side. In the left side you may find data input, and which is also as serial, and in the right side you may find data output, which is also in serial. And in the lower side of the figure you may find there are data input, and which is also parallel. And in the upper side of this figure you may find data output, which is also parallel. And also the directional movement of the data through a shift register can be either to the left shifting, to the right shifting, left in but right out rotation, or both left and right shifting within the same register, thereby making it bidirectional. So let's move into the next slide. From this slide, we may learn the design of 3-bit serial in, serial out. So let's begin. Let all the flip-flop be initially in the reset condition, which means the value of Q2, Q1 and Q0 or Q0 is equals to 0. If an entry of a 3-bit binary number 111 is made into the register, this number should be applied to serial data in, which is symbolized as D subscript serial underscore in bit with the LSB bit applied first. The data input of first flip-flop, which means D2, is connected to serial data input D serial in. Output of the first flip-flop is symbolized by Q2 is connected to the input of the next flip-flop, which is second flip-flop, and the output of and the input of the second flip-flop is symbolized as D1, and similarly so on. So let's move into the next slide to explore the block diagram of 3-bit serial in and serial out. Well, this slide represents the block diagram of 3-bit serial in and serial out of shift register. And if you look at this figure, then you may find there are 3 flip-flop, which is named as first flip-flop, second flip-flop, and third flip-flop. And each flip-flop has one input as well as one output. And the first input the first input of the first flip-flop is symbolized as D2, and the first output of the first flip-flop is symbolized as Q2. Similarly, D1 and Q1 for second flip-flop input and output, and similarly D0 or D0 and Q0 for the third flip-flop input and output. And in the left side of the first flip-flop you may find there are data in, which is serially, because we are designing, or we are gonna design serial in, serial out. That's why we may find in the right side of the third flip-flop, or you can say the output side of the third flip-flop, data output or data out, which is also serial. And another important thing you need to notice from this figure that a clock pulse is applied at each flip-flop, which is symbolized as clock, and another thing which is also same for the for three for this flip-flop, which means the same clock pulse is applied for the three flip-flop. So that's all from the block diagram of 3-bit serial in serial out shift register. So let's move into the next slide. Well, this slide represents the operation of 3-bit serial in serial out. So let's begin. Before application of clock signal or before apply of clock signal, let the value of, sorry, I repeat it again, let the value of Q2, Q1 and Q0 or Q0 is equals to 0, 0, 0, and apply LSB bit of the number to be entered to D serial in. In that case, the value of D serial in is equals to the value of D2, which is equals to 1. And if you this hypothesis or this statement is also shown in the figure, and if you look at the first flip-flop, then you may find the value of D serial in is equals to 1. In that case, the value of D2 is equals to also 1, and the value of Q2 is also 1. Well, apply the clock. Now we need to apply the clock in that case on the first falling edge of clock, which means we are applying the first negative clock edge is applied at the clock pulse. In that case, the first flip-flop is in set condition, and stored word in the register is Q2, Q1, Q0 is equals to 1, 0, 0. Okay. Since the value of Q2 is equals to 1, but if you guys look at the second flip-flop, you may find the value of Q1 is equals to 0, the value of Q1 is equals to 0, and the value of Q0 is equals to also 0, because the previous state, initially the value of Q2, Q1 and Q0, both the among the output, all the values of the outputs are 0 initially, but when the first negative clock edge is applied to the clock, at that moment the value of Q2 is equals to 1, but the value of Q1 and the value of Q0 remains the same as previous. So let's move into the next slide to explore what will happen when the negative clock edge is applied at the clock. So let's move into the next slide. So this is this slide represents the second condition, which means when the second negative clock is applied at the second clock. So let's begin. Apply the next bit to D serial in. So D serial in, the value of D serial in is now 1. Well, as soon as the next, which is equivalent to second negative clock edge, is applied to the or at the clock, then second flip-flop will set. Remember these things. When the first negative clock edge is applied at the clock, in that case the first flip-flop is set condition. But when the second negative clock edge is applied at the clock, in that case the second flip-flop is only in set condition, and the stored word change to Q2, Q1, Q0 is equals to 1, 1, 0. Okay, so if you guys look at the first flip-flop, then you may find the value of D serial in is equals to 1. In that case, the value of D2 is equals to also 1, and the value of D2 is equals to also I repeat again, and the value of Q2 is equals to also 1. And since the second negative clock edge is applied at the clock, in that case the second flip-flop is in set condition. In that case, the value of Q1 is equals to 1. Okay, and the value of Q0 is equals to 0, because the previous state value is 0. That's why this value is not changed as but remains as previous. So that's all from the second condition. Now we need to move into the next slide to explore what will happen if the third negative clock edge is applied at the clock. So let's move into the next slide. So this slide represents another condition, which means the third negative clock edge is applied at the clock. What will happen? So let's begin. Apply the next bit to the I repeat it again. Apply the next bit to be stored, which means 1 to D serial in. Apply the clock pulse as soon as the third negative clock edge is applied at the clock, or you can say as soon as the third negative clock edge is hits, then the third flip-flop will be in set condition and the output will be modified to Q2, Q1, Q0 is equals to 1, 1, 1. So let's see from the figure what we are gonna found, or what we are understand from this statement. If we look at the figure, then you may find the value of D serial in is equals to 1. That's why the value of D2 is equals to also 1, and the value of Q2 is equals to also 1. Since the value of Q2 is equals to 1, in that case the value of D1 is equals to 1. In that case the value of Q1 is equals to also 1. But in the third flip-flop, we know, since in this case the third negative clock edge is applied at the clock, that's why the third flip-flop in set condition. That's why the previous value of Q0 is not remain same in this condition. The value of Q0 will be replaced by 1 for this condition, because third negative clock edge is applied at the clock. That's why the third flip-flop is in set condition. So that's all from the condition. So let's move into the next slide to explore the truth table of this design. So this slide represents the truth table of 3-bit serial in and serial out. And if you look at the header section of this table, then you may find there are I repeat it again, there are 5 columns which is named as clock, D serial in, which is equivalent to Q2 because D serial in is connected to D2 and which is connected to Q2. That's why we can write D serial in is equals to or equivalent to Q2. And in the after this we may find Q2 is equals to D1 because Q2 is connected to D1 and Q1 is connected to D0. And in last or at last we may found Q0. Well, condition and nature. Initial condition, as we have already known that the initial condition of the design is, or if we can say the value of Q2, the value of Q1 and the value of Q0 is equals to 0, initial condition. But when the first clock edge is applied, in that case the value of D serial in assigned 0, which is shift to the right or serial. That's why we may found the value of Q2 is equals to 1. But in case of second flip-flop and the third flip-flop, the value are assigned from the previous state. That's why in here you may find the diagonal arrow, which is represents the first 10 from the previous situation, and the last 10 are represented as the present condition. That's why we have placed this arrow as diagonally from previous to present state. And that's all from the truth table of 3-bit serial in and serial out. So let's move into the next slide to explore another design mechanism which will come after the waveform of this design. So let's move into the next slide to explore the waveform of 3-bit serial in and serial out. Well, this slide represents the waveform of 3-bit serial in and serial out. Well, since there are 3 clock age of this design, and all our clock age is negative, and 3 clock age means first, second and third, and which is represented as clock signal. Well, after that we placed the value, the D serial in, which is initially 000. After that we assign, or you can say the first negative clockage is applied. That's why we may found in the stored data in Q2 is 100. After that, when the second or second negative clockage is applied, in that case the first second flip-flop is the second flip-flop is in set condition. In that case we may found the stored data is 110, and in the last, or you can say that when the third clockage is applied or hits the clock, in that case the third flip-flop will be or is in will be in set condition. In that case we may found the stored data is 000. So that's all from the design mechanism, and now we need to move into the next slide to explore another design, which is 3-bit serial in parallel out. So let's move into the next slide. Well, this slide represents the design mechanism or the starting of design mechanism of 3-bit serial in parallel out. So let's begin. Let all the flip-flop be initially in the reset condition, which means Q2, the value of Q2 is equals to the value of Q2, the value of Q1, and the value of Q0 is equals to 0. If an entry of a 3-bit binary number 110 is made into the register, this number should be applied to serial data in, which is symbolized as D serial in bit, with the LSB bit applied first. The data input of first flip-flop, which means the input of the first flip-flop is symbolized by D2, is connected to the serial data input, which is symbolized by D serial in. Output of the first flip-flop, which is symbolized as Q2, is connected to the input of the next flip-flop. Next flip-flop means second flip-flop, and which is also symbolized by D1. And similarly, in this way, the rest of the flip-flops. The data is entered serially and taken out. I repeat it again. The data is entered serially and taken out in parallel. Data is loaded bit by bit. The outputs are disabled as long as the data is loading. As soon as the data loading gets completed, all the flip-flops contain their required data. The outputs are enabled so that all the loaded data is made available over all the output lines at the same time. You guys need to remember or read carefully in the second passage for the design purpose. So let's move into the next slide. Well, this slide represents the block diagram of 3-bit serial in parallel out shift register. And if we look at this figure, then you may find there are 3 flip-flops named as first flip-flop, second flip-flop, and third flip-flop. And all the flip-flops have all the flip-flops or each of the flip-flops has one output and as well as one input. Well, or you can say one input as well as one output. Well, and if you look at the first flip-flop, then you may find there is one input and one output, which is symbolized as D2 and Q2 respectively. And if you guys look at the second flip-flop, then you may find there is also one input and one output also, which is symbolized as D1 as well as Q1 respectively. And this way in this way the third flip-flop are as in sequence, which means the value of the third flip-flop has also one input as well as one output, which is symbolized as D0 as well as Q0. And one important thing you have to This slide represents the operation of 3-bit serial in parallel out. So let's begin. Before application of clock signal, let the value of Q2 is equals to 0, the value of Q1 is equals to 0, the value of Q0 is also 0, which means Q2, Q1, Q0 or Q0 is equals to 0, 0, 0, and apply LSB bit of the number to be entered to D serial in. Well, in that case, the value of D serial in is equals to the value of D2, the value of D2 is equals to 0, which means actually D serial in is equals to D2 is equals to 0. Now we need to apply the clock pulse at the clock, which means the first negative clockage or the first falling edge of the clock is applied at the clock. In that case, the first flip-flop is set condition and stored word in the register is Q2, Q1, Q0 is equals to 0, 0, 0. And if you guys look at the figure, then you may find the value of D serial in is equals to 0. That's why the value of D2 is equals to 0 and the value of Q2 is equals to 0. But for the first flip-flop, you need to remember one important thing, which is since in this case the first negative clockage is applied at the first flip-flop, that's why the first flip-flop is in set condition and the rest of the flip-flop are consume or resume the previous value in this condition, which means the present value of the present value of the outputs of the second and third flip-flop is equals to the previous value of the outputs of the second and third flip-flop, actually, which means the value of D1 is equals to 0. That's why the value of Q1 is equals to 0 because the previous state, and similarly for the third flip-flop. So that's all for the first condition. So let's move into the next condition to explore what we're gonna found if the second negative clockage is applied at the clock. Well, this slide represents the another condition of the design mechanism of 3-bit serial in and parallel out. So let's begin. Apply the next bit to the serial in so that the serial in, the value of the serial in is equals to 1 as soon as the next, which means the second negative clockage of the clock is applied, or you can say that sorry, I repeat it again, or the second negative clockage of the clock. Second negative clock edge is applied at the clock pulse. In that case, the second flip-flop will be in set condition, like the previous slide, or like the previous operation, or like the previous condition. And the stored data would change as follows, which is Q2, Q1, Q0 is equals to 1, 0, 0. Well, and if you guys look at the figure, then you may find the value of D serial now 1, but previously it has 0. That's why the value of D2 is equals to 1 and the value of Q2 is equals to also 1. Well, and since the second negative blockage is applied at the clock, in that case the second flip-flop is in set condition. In that case, it may hold the previous value, and the third flip-flop also consume the previous state value, which is the value of D1 is equal to 0, the value of Q1 is equal to 0, and the value of D0 is equal to 0, and the value of Q0 is also 0. So let's move into the next slide to explore another condition, which means when the third negative blockage is applied at the clock, what will happen? So this slide represents the third condition, which means the third negative blockage is applied at the clock. So let's start. Apply the next bit to be stored, which means 1 to the serial in, which actually means the value of the serial in is equal to 1 right now, or for this condition. Apply the clock pulse, which means third negative blockage is applied at the clock. As soon as the third negative blockage hits, then the third flip-flop will be in set condition and the output will be modified to Q2, Q1, Q0 is equal to 110. Well, if you guys look at the figure, then you may find the value of D serial in is equal to 1. That's why the value of D2 is equal to 1 and the value of Q2 is equal to also 1. Well, and if you look at the second flip-flop, then you may find since the Q2 is connected to D1, that's why the value of D1 is equal to 1 and the value of D1 is equal to also 1. And if you guys look at the third flip-flop, which is in set condition for this criteria or for this situation, because the third clock edge is applied at the clock, that's why the third flip-flop is in set condition. That's why it may consume or resume the previous state value, which is the D0 value is 0 and the Q0 value is 0. So that's all from the operation section. So let's get into the next slide to explore the truth table of 3-bit serial in parallel. Well, this slide represents the truth table of 3-bit serial in parallel output. And as this truth table is similar, it's quite similar. Is quite similar from the 3-bit serial in serial out shift registers. And if you guys look at the first condition of the clock and the nature of this condition, which is negative clock edge, which is falling edge, also which is also known as falling edge clock pulse. In that case, the value of the serial is shift serially to the first flip-flop. The value of this serial is equal to this serial in is equal to 0, and the shifted value is 0 also, and it is the output value of the first flip-flop to be symbolized as Q2, and the value of Q2 is equal to 0. But for the first condition, second flip-flop and the third flip-flop remains or resume or consume the previous state value. That's why here the arrow is presented or represented diagonally to represent the bottom end of the arrow is represented to previous state, and the arrowhead represents at the present state. So I hope you guys don't have any problem or confusion regarding this issue. And in this way, the second condition and the third condition. So that's all from the truth table of 3-bit serial in parallel out. Now we need to move into the next slide to explore the waveform of 3-bit serial in parallel out. So let's move into the next slide. So this slide represents the waveform of 3-bit serial in parallel out. Well, and this figure is also similar to the previous one. That's why if you guys look at the clock signal, then you may find there are 3 clock edge, or you can say there are 3 negative clock edge, which is actually down falling edge or down arrow, which is also numbered as 1, 2, 3. And in the right section, you may find what kind of data are stored by this individual flip-flop, or you can say as a whole shift register. So if you guys look at the D serial in, which is at initial condition, which is stored only 0, 0, 0 data. But if you look at the Q2 also, which is also similar to the D serial in, which is also consumed or stored 0, 0 data. And if you guys look at the first output If you just look at the output of the second flip-flop, then you may find there the stored data is, the value of stored data is 100, and the output, the value of the, if you guys look at the output of the third flip-flop, then you may find the stored data, the value of stored data is 110. So that's all for the 3-bit serial in and parallel out. So let's move to the next slide to explore some of the advantages and the drawback of shift registers. There are several advantages of shift registers, such as they are operate faster than the logic circuits in converting serial to parallel and parallel to serial interfaces. Next one, pseudo noise sequence number in code division multiple excess is generated using them. They are easy to design as it reduces the amount of wiring and occupy less space. They are helpful in tracking the information, which is data. Delaying a signal is easy. Data encryption and decryption can be achieved using linear feedback shift registers. And there is one disadvantage. Sorry, I repeat it again. There is one disadvantage, or you can say one major drawback of shift register, which is actually the output current of register is limited. Now, time has come to learn some of the applications of shift registers. That's why we need to move into the next slide. There are several applications of shift registers. They are basically used for data transfer and temporary data storage. They are implemented in devices like computers and calculators, as they serve as temporary data storage spaces. Next one, they are used to handle data processing in the former years of computer technology, such as shift right and shift left, arithmetic shift right and left, rotate right and left were supported by the processor. Next one, they are used to add more binary inputs to a microprocessor, as it has fixed number of input or output pins. They are also used as delay circuits. They are used as sequence generator and counters. In digital transmission, they act as parallel to serial converter at the transmitter end, which is actually multiplexing, and serial to parallel converter at the receiver end, which is actually which is actually demultiplexing. In the next lecture and in the next week, you guys will know about parallel in and serial out shift registers. So let's move into the next slide. That's all for this lecture. Thank you guys for your attention. See you guys in the next lecture. Till then, thank you.